Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. All right, we have finally reached a kind of ultimate part of polynomials here. So everything you've seen, watched, whatever we've done prior to this moment, you've dealt with polynomials, factoring them, that type of thing, graphing polynomials, talking about the end behavior of polynomials, the zeros of polynomials, the multiplicities of those zeros, graphing polynomials using that information. We also talked about dividing polynomials using synthetic division, and finally the remainder and factor theorems. Now we get to kind of the last stage with polynomials. Well, I would say really it's the penultimate stage because there's one more stage beyond this, but for right now we'll think of it as kind of the ultimate stage. Real zeros of polynomials and the rational roots theorem. This video is going to be dedicated not to using the rational roots theorem. If you're looking for that, I would go to the next video. Instead, I would love it if you stuck around for a motivation of the rational roots theorem, because if you're heading into calculus, you need to be at this level of critical thinking before you set foot into a calculus course. So let's talk about this. There are an infinite number of algebraic expressions that you simply cannot factor, or seemingly cannot factor. For example, this guy right here. Now, we dealt with a quintic polynomial last lecture, if you're following my lectures in the order that I've posted them. And I gave you hints on that polynomial. I think that polynomial, it was something like, one of the hints was x equals 0 was a 0 for that polynomial, and x equals 1 was a 0 of multiplicity 2, which allowed us to factor out these factors like this, right? So we do get that from that last video. However, in this problem, or at least with this polynomial, we're not given that information. As such, factoring this is going to be very challenging. If it was a binomial, we could treat it as, let's just say there were only two terms. We have either a difference of squares, or it could be a sum or difference of cubes. That's our only way to factor a binomial. Well, other than factoring on a GCF. If it was a trinomial, we have a bunch of different methods we could use to factor trinomials. So again, initially factoring on the greatest common factor, but beyond there, some people use a guess and check method, some people use an AC method, a diamond method, a box method. We've learned a lot of ways up to this point on how to factor a trinomial. If it was a quadrinomial, which means that you have 4 terms, well, we would factor using grouping. And that's just a method we learned from way back in elementary algebra, which is also known as Algebra 1. This guy right here, though, is none of those. Oh, by the way, I think that's good enough to say. This guy is none of those. So this, factoring this bad boy right here, is going to be a bit of a mess. This is different because it's a quintic, and it has more than 4 terms. So factoring by grouping might be a little challenging. And it turns out that once you get beyond a certain degree with polynomials or a certain number of terms, there really aren't very many closed forms as far as factoring goes. So what makes this so different than all previous methods? Just the number of terms. For those who want to go into mathematics as a career, you'll know that, or you will find out that there are some methods for factoring large polynomials like this, but they're super complicated, very complicated, not worth memorizing. So let's go ahead and motivate a brand new factoring method. Now, I should let you know that this factoring method does not always work, but it is actually a very powerful method. It'll work for the most part if you have roots or zeros to this polynomial that are rational. And that'll also give us the name of the method when we get there, which is called the rational roots theorem. So in this case, a little color is going to go a long way. So what I'm going to do is just add a little splash of color here. I'm going to go ahead and maybe highlight the, whoops, that's not a highlighter, is it? I'm going to go ahead and highlight the last number, or the last term there, which is the constant. I'll highlight that in yellow, and I'll highlight the coefficient of the first term, which we call the lead coefficient, in blue. So this is just because of how we're going to motivate the method. Now, notice that I don't really care about the sign of the constant term. Actually, you probably don't notice that, but I'm going to tell you, I don't really care about the sign of that constant term. I'm going to really pretty much throw that out. It doesn't really matter for me. Now, without telling you how I did this, I'm going to pre-factor this so that we can motivate the method. So I'll pause the video and I'll show you the actual factorization. And here we have the full factorization. You probably don't believe me, so you want to go ahead and multiply that back out, but I promise you that is exactly what the factorization is. And I want to draw your attention to some very important numbers here. The coefficients on each of those x's in the linear factors, the 3x, the 1x, actually the coefficients are actually 3, 1, 1, 7, and 1. If you were to multiply out all those factors, all that mess on the right hand side, the stuff that creates the 21 in blue there, well, that's going to be the product of all these lead coefficients. 3 times 1 times 1 times 7 times 1, that is a 21. So that's just to let you know that that's how you get that lead coefficient of 21. It's the product of all the lead coefficients in the linear factors. And that's still, I'm not telling you that's how I created that factorization. I'm just telling you that's a fact. And likewise, let me go ahead and bring out my yellow highlighter. The product of all the constants here that I'm highlighting, all of those should multiply up to be a 36. So 2 times 1 times 2, well, that's 4, times a 3, well, 4 times 3 is 12, times another 3 will be 36. So that's kind of to justify, not justify, but to start the motivation of the rational roots theorem. Again, you have no clue how I actually factored this, and I'm not going to tell you yet. But what I do want to do at this point is factor out each of these non-unit lead coefficients. That is, if I have a coefficient on x that's not 1, I want to factor it out of that linear factor. So I'm going to pause the video and do that so you don't have to see my handwriting over and over again. And I want to justify everything I've done here. So if you look in that first factor, this factor, I'll just point at that first factor right there. If you were to factor a 3 out of that, remember factoring is the same thing as division. So 3x divided by 3 is going to give me the 1x that you see right here. And then a negative 2 divided by 3 is going to give me that negative 2/3. Again, in that fourth factor, I'll just point and arrow at it right there. If you were to divide out a 7 from both of those terms, you'd end up with a 1x minus 3 over 7. And that is right here. There you go. Now what I'm going to do is go ahead and highlight again, just so you see, I'm going to highlight a few things here. And what you see, again, all I did was highlight the 2, the 1, the 2, the 3, the 3. Those are the products that create that 36. The stuff in yellow is still the same stuff in yellow. What you should notice is when I factor out that 3 and I factor out that 7, I'm no longer highlighting the 3 and the 7 that create the 21 that'll be pulled out front. Instead, I'm highlighting the denominator, which is 3, and the denominator, which is 7. Still the same 3 and 7, to be honest with you. But remember, 3 times 7 will be that blue 21 on the left-hand side of the screen. Now, all I'm going to do now is kind of collect the 3 and the 7 out front. So I'll just pause the video and do that. And at this point, you should really notice I actually painstakingly went through and wrote all those numbers, like in the second factor, the positive 1, and the third factor, the negative 2, as fractions. 1 over 1, negative 2 over 1, negative 3 or positive 3 over 1 in the last factor there. And I also, again, still highlighted in yellow, the products that create 36, 2 times 1 times 2 times 3 times 3, and the products that will create the 21, the 3, the 1, the 1, the 7, and the 1. So this is what is critical to note. And we should also remember that the factor theorem states that C is a zero of a polynomial. In fact, let me write that down. So recall from the factor theorem, C is a zero of your polynomial if and only if x minus c is a factor of your polynomial. Now look at all those factors of our polynomial. And now let me restate that, that sentence. Look at all those zeros of that polynomial. I mean, they are factors, but remember, if x minus 2/3 is a factor, then 2/3 must be a zero. Thus, the zeros of the polynomial that we were handed must be 2/3, because x minus 2/3 is sitting there, -1/1, which is just -1, and that's because x minus a -1, which is x plus 1, is sitting there, 2/1, which is because x minus 2 is sitting there, and 3/7 because x minus 3/7 is a factor, and finally 3/1 because, oops, that should be a -3/1. Let me write that in there. There we go. A -3/1 because x minus a -3/1 is also a factor. Now I need to draw your attention to something. Remember those two numbers that we highlighted at the very beginning, the 21 and the 36. Let's take a look at those. I'm going to scroll up, which means my screen will go wacky, and I've taken the liberty to write down the 36 and the 21 here, again with the same colors that we used before, and a bunch of numbers. Now let's think about those numbers. If I wrote 36, actually let's concentrate on the 21, it's a little shorter list, right? 21. So then I write ±1 and ±3 and ±7 and ±21. What do all those numbers have in common with 21? Well, if you said that they all divide into it, you are absolutely correct. They divide nicely into 21. And the same thing with all those numbers highlighted in yellow. 1, 2, 3, 4, 6, 9, 12, 18, and 36 all divide into 36. Those are called the factors of 36 and the factors of 21. And this actually motivates how we got our zeros. Notice our zeros there. The very first zero is 2/3. And notice, I'm going to underline them in red, 2/3. Notice the second one is 1/1. And I did the double underline so you can see that which ones I was talking about. The next one is 2/1. Well, now I can't really do double underlines, can I? So maybe I'll use a different color. So 2/1. And the next zero is 3/7. Well, look at this. I have a 3 here and I have a 7 here. And finally, a 3/1. And it'll just get messy if I draw it. So I'm going to write it up above if you don't mind. A 3 over that one. But the reality is that turns out those numerators are found from the factors of 36 and those denominators are found from the factors of 21. So it looks to be the case that the zeros for this polynomial are just ratios of factors of 36 and 21. And they are. So let me scroll up. And I just want to draw your attention to the fact that 36 was the constant term and 21 was the lead coefficient or leading coefficient, just depends on who you talk to, how to say that. But the 36 came from the constant term and our numerators for our zeros were factors of that. And our denominators, for our zeros were factors of the leading coefficient. And that is called the rational roots theorem. I'm going to scroll down a little bit and just write it first in English, and then we'll go and actually see the theorem itself. Thus, it appears to be the case that the zeros of a given polynomial are just the ratios of factors of the constant term to the factors of the leading coefficient. Now, I do want to mention here, if you look at those factors of the constant 36 that are listed out in yellow right up above there, we didn't use all of them. And also, we didn't use all the factors of the leading coefficient either. So many of those get ignored. This is a case-by-case basis. You have to test a few of them. Hopefully you find enough to find all your factors. That's really how this theorem works. It's sort of like a shooting in the dark. Well, sort of. You have little hints as to what your zeros might be because they're just ratios of factors of the constant term to the factors of the leading coefficient. And I should kind of clean that language up a little bit down below, but I kind of feel like the theorem does a great job at that. So here's the formalized statement of the rational roots theorem. Given a polynomial, and the restriction on this polynomial is it must have integer coefficients, then every rational zero of the polynomial is of the form p over q, where p is a factor of the constant term, which is what we were saying before. We actually used the yellow to highlight that, so I'll do that here. And q is a factor of the leading coefficient of the polynomial, which I'll again use blue to highlight that. Now there are a few key words going on here. First of all, the fact is you must be dealing with a polynomial. The second condition is that that polynomial must have integer coefficients. And finally, this theorem only gives you the fact that every rational zero, which means every zero that can be written as a fraction, is of the form p over q. So the rational zero is the key couple words there. Now, does this theorem actually give you those zeros right from the get-go? No, you have work to do. It doesn't magically hand you how this factors. It doesn't magically hand you the zeros. You have a little bit of a challenging work to do. And to showcase that, I'm just going to hop back to the previous example here and show you how challenging it may look to be. I say look because there are tactics to help us out. So there is our original polynomial, and we're looking for factors of 36 divided by factors of 21, and those are candidates for zeros for our polynomial. Now, we listed out all the factors. Let me show that. And there were quite a few. I even said, like, man, this is quite a few factors of 36, quite a few factors of 21. Our candidates for the zeros for our polynomial are the following. And what you see before you is a list of all of the ratios of factors of the constant term to the factors of the leading coefficient. Notice those denominators are factors of the leading coefficient, 1, 3, 7, and 21, and the numerators are all the factors of 36. And you look at that and say, oh, you should, because that's a lot of options. And you have to test all those to see which ones are actual zeros. Remember, you can find out the zeros of a polynomial by using the remainder theorem, actually. So if you use the remainder theorem in synthetic division, you can find out if 1 is a 0 by using synthetic division on the polynomial and finding out that the remainder is 0, for example. But it seems like such a huge list. Why would you ever want to use this for factoring? Well, there are a few tricks here. One, there's a lot of repeats here. For example, 3 over 3. That's 1. So I'm going to go ahead and just erase that 3 over 3. And 6 over 3. That's 2. So I'm going to erase that. We already have that one. And 9 over 3. Well, that's 3. 12 over 3. That's 4. 18 over 3 is 6. We already have that. And 36 over 3 is 12. We already have that. But still looks horrendous, right? Well, and as far as the sevenths go, there's not a lot of help with the sevenths. They're all viable candidates. And finally, the 21st. Well, 3 over 21, that's the same thing as 1/7. We already have that. 6 over 21, that's the same thing as what? 2 over 7, and we already have that. 9 over 21 is the same thing as 3 over 7. We already have that. That's 4/7 right there. That's 6/7. We already have that. And 36 over 21, 3 goes into both of those. That's 12/7, and we already have that. Well, still. Yes, I got to erase some of those, but it's still pretty brutal, right? I mean, that's a long list of numbers. Here's the deal. You will always try the simple integers first. That's a great idea because you're doing synthetic division to find out which of these are actual zeros. Let me actually write that down. So to test if a rational or a ratio is a 0 for our given polynomial, we're just going to use synthetic division and the remainder and factor theorems. Synthetic division gives us that P over Q, and we'll write out the coefficients of our polynomial in this big old list there. And then use synthetic division. If the final term after synthetic division is 0, then, or in other words, if the remainder is 0, then x minus P over Q must be a factor. And this is why I say the trick really is to list out a few of the zeros, or I really should say candidate zeros. And usually you're going to list out the easiest one and the easiest ones and the smallest numbers too. It's just easier to start with small numbers. So you list out some of the smaller numbered zeros here. I'm going to use a different highlighter because I've used that same yellow and blue throughout. So if it was me and I was hunting for zeros of this polynomial, I would definitely try synthetic division to hunt for zeros on this guy, and on this guy at least. Notice I didn't highlight all of them. I just started with those three, because those three actually lead to 6. I'm testing plus or minus 1, plus or minus 2, plus or minus 3. If those fail, I continue forward. I don't go much beyond maybe that 6 there, because once you start going to larger numbers, synthetic division gets ugly. If I still haven't found a 0 by that time, I then will dip into the 1/3, maybe the 2/3, then the 1/7, maybe the 2/7, then the 1 over 21. If you still haven't found a 0 by that point, then you're really in bad shape because you're going to have to go through more of these. But generally speaking, you can get a little bit of luck by going through some of the smaller numbers first. And note here that our original polynomial was degree 5, right? So if you happen to get 2 different zeros, you've now reduced it down to a degree 3 because you've removed 2 of the factors of the linear factors. So it went from a degree 5 to a degree 4 when you found the first factor, and then it'll go from a degree 4 to a degree 3 with the second factor. And you might be able to, with a cubic, do factoring by grouping for the rest of it. If that doesn't work, or if you found 3 zeros, you can use you can factor the remaining quadratic. So there are a lot of little tricks to doing this to speed up the process. And trust me when I tell you that students actually get pretty proficient with this, and they look fondly back upon this. That's kind of a lie. They don't at all. The final thing I want to mention before I stop this video is that the proof of the rational roots theorem is going to be left for a completely separate video. It's not that it's a terribly hard proof. Actually, it's not bad at all. But I think right now, just that idea of the rational roots theorem is important enough. I'll prove it in the next video, and then we'll take some examples.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.